Hello student, to the Foundation of Classical Electrodynamics course. So today we will have lecture 17 where we discuss delta function, which we already introduced in the last class. Today we have class number 17. And we discussed delta function last day, so that we are going to continue. So delta function by definition, as it says that delta x is 0 when x is not equal to 0 and delta x become infinity when x is equal to 0, and if I integrate the entire x axis in one dimension, this is give us 1 finite value. Better to write 1 in a normal way because this looks quite matrix kind of thing. So simply 1. So these are the three basic properties, not properties, this is by definition, this is the delta function. And also we find that in general a function if I want to find out this integral, then it gives us this. Last year also we try to understand few properties of the delta function. One very important property was delta of Ax is equal to 1 by mod of A. We prove it actually. This, the consequence of this expression tells us delta of minus x is equal to delta of x. Yeah, that is. So today we are going to extend our discussion on delta function. This is a very important function in electrodynamics and also in other branches of physics. So I thought that I should take some elaborate I should give some elaborate discussion on delta function. So now today we will going to discuss three-dimensional delta function. So far we are dealing with one dimensional delta function, but three dimensional delta function we will do today in detail. So normally we represent this three dimensional delta function as delta 3. In the argument we write vector r, and that is simply in Cartesian coordinate system the multiplication of 3 delta function with this, where r is a simple position vector. Okay. Now if I want to integrate this delta function, delta q r vector dV over entire space V. So, this is all space. Then this is simply minus infinity to infinity, then we have minus infinity to infinity, and then minus infinity to infinity, delta x, delta y, delta x, and the volume element dx, dy, and dz, that is equal to 1. That is the property. Well, now if I integrate this over a function in all space, that we do in one dimension for all space, and then integrate this function we will simply have function evaluated at r prime point. Okay. So, this is the 3-dimensional way to represent delta function in Cartesian coordinate system. However, we can generalize this in other coordinate system, but the thing is, again we need to deal with the scale factor that we learned in curvilinear coordinate system. So, in curvilinear coordinate system, so in curvilinear coordinate system, what happened that we have the variable u1, u2, u3, and the volume element there, if I define the volume element, this volume element, if you remember, this is h1, h2, h3, and d u1, d u2, and d u3. This is the way we define the volume element. Okay, this is the volume element in curvilinear coordinate system. Well, if I now define the delta function here, so in general the delta function in 3D, if I integrate it over all space, and it is like delta 3 r minus r prime dv, that is equal to 1, which I mentioned in the last class, that from where we can find out the unit of this delta function, if somebody want to ask what should be the unit. So, from this expression you can tell that delta cube r minus r prime, the unit is 1 by volume here. Okay, and in general when we define the delta function in this curvilinear coordinate system, so delta cube, then r minus r prime, we should have here the right hand side, this is the general form, 1 divided by h1 h2 h3, and then delta u1 minus u1 prime, delta u2 minus u2 prime, and delta u3 minus u3 prime. So, this is the general form of the delta function in any coordinate system, in curvilinear coordinate system I just mentioned. So, then if I now represent a cylindrical coordinate system, then the delta function should be in cylindrical coordinate system. If I represent the delta function, sometimes the function is given in the cylindrical coordinate system with the delta function, and in that case you need to use this. So, it suggests that it should be 1 divided by rho, because if you calculate the scaling factor h1 h2 h3, this 3 multiplication give you 1 by rho. We discussed this several time in earlier class. So, it should be delta rho minus rho prime, delta phi minus phi prime, and delta z minus z prime. In the similar way, in cylindrical coordinate system, if this is the case, then in spherical coordinate system, spherical polar coordinate system, I can define this delta function having this 3-dimensional form, and there I should have 1 divided by r square sin theta, because the scaling factor you need to calculate. If you go back here, the scaling factor is here 1 divided by h1 h2 h3. So, h1 h2 h3 if you multiply in case of spherical coordinate, then it should be r square sin theta. Then delta, we should have r minus r prime, delta theta minus theta prime, and delta phi minus phi prime. So, this is the way we can define the delta function in cylindrical coordinate system and in spherical coordinate system. Well, after that now we try to understand the delta function, but with another identity we will try to derive. But before that, let us quickly do few problem regarding delta function as an exercise. So, we will have problem 1, and this problem 1 is saying that find out the value for all space the function is defined in this way. This is r square minus 2 r dot a and plus a square, and then you have delta cube r minus a dv. This is so we know that the delta function means simply if this is the case, it is given in as a function of r. So, when we have the integration like function as a vector r, and then delta cube r minus a dv, we simply put if this is for all space, then we simply have this. So, we are going to use that. So, whatever the integration we have here, that overall space. So, V is overall space. So, that thing should be equivalent to simply by replacing a in place of r. So, we have r square here. So, it should be simply a square, then simply a square, and then we have minus of 2 vector a dot vector a, because there it was vector r dot vector a. I just replace r to a, and then plus a square. So, this quantity is simply 0. Okay. So, this integral should be 0 when we try to calculate for all space. Problem 2. In problem 2, we have a similar kind of problem. Here we have integration v, and then the function is r vector r minus vector a mod square, and I want to evaluate delta, and in the argument it is minus 2 vector r over dv. Now, this v is defined here. This v, this space is defined here, and it is saying that this is a sphere of radius 4. So, in the space we are integrating these things of a sphere of radius 4, and now a vector is also defined, a vector is also given, that is important, and this a vector is I plus j plus k. Okay. So, now first we need to check that this a vector, where the delta, I mean this what is the magnitude of this a vector. First let us find. So, the magnitude of a vector is root over 3. This quantity, if you calculate, it is less than 4. So, that means if the a is I mean that means we whatever the integral we want to calculate, inside that the a sits. So, then the integration, if I calculate this integration, we can have this volume, which is the sphere of radius, 4, and this quantity r minus a square of that. Now, here inside the delta we are having minus 2 r. So, that is something. So, we already had the vector the delta identity regarding delta, and that is delta Ax was 1 divided by mod of A and then delta x. If I want to get rid of this constant, then that is the relation. Now, it is delta cube here sitting. So, that means here if we have delta cube, then this quantity, when we have delta cube here, so this quantity should be multiplied by, it should be a cube here. So, I should have 1 divided by mod of 2 cube, because it is 3 dimension delta cube, and then I have delta r and dv. Okay. So, now life is simple. So, now I can take this 1 by 8 outside, and rest of the integration is straightforward, because integration r minus a square of that and delta r dv. So, that is the standard integration we are having, delta function with a function. So, I just replace here r equal to 0, and then whatever we get, that is the result. So, if I put r equal to 0, we have simply 1 by 8 multiplied by, if r equal to 0, if I put, then it should be 0 minus a vector and then mod square. So, mod of a vector we already calculated, and that is root over of 3. So, this quantity is simply gives me 3 divided by 8, that is the value of this integration. Okay. So, this is a typical kind of problem that you can use. If I put a simple function in one dimension and then put a delta function, then you just simply replace this argument, whatever the argument here is 0, and then we can find out the values. But there is some problem where instead of having a simple x here, you can have a function. So, if that is the case, then how to deal with this issue? So, that I will now going to do. So, another important identity, another very important identity regarding the delta function is this, which is useful when we have the, instead of having delta, for example, delta x, instead of having delta x, you are having some kind of functional form like x square minus 1 in the argument. So, then how to deal with this kind of delta function, that is in question. So, in order to handle that, so let us understand this identity. So, the identity is saying that if we have delta, say function of h, which is a function of x, then what happens? So, we are having delta function and inside the argument we have another function. Okay. Inside the function we have another function. So, you can understand this in this way. I just simply try to derive this. So, let me first write down the result here. What should be the result? The result should be summation over k 1 divided by mod of h prime is the derivative of this function, and I put x k, where x k is the roots of this equation. Whatever the equation we have, if we find the root where this function vanishes, that value, and then delta x minus x k, under the condition that when you put the root of the derivative of this function, this thing should be not equal to 0. This thing should be, otherwise this and since it is a root, x k is a root, so we have h x k is equal to 0, because this is a root. So, we can have a function, if I consider this function h k, so we can have a polynomial kind of function having multiple 0. So, these points, so I am plotting x here, and in this side I am plotting h, which is a function of x, and try to find out this quantity delta. In the argument we have the function h, this one, and we want to figure out what is this. The result already I written. So, the point is these are the roots, say x1, x2 and so on. So, this is my kth root suppose. So, these are the roots where the function vanishes. If you know that, then you just put the value, you just make a derivative of this given function, put the value of the these roots there and make a summation, and that should be your result. So, you can quickly prove it by just expanding this h. For example, if I expand this h x, if I expand this, so it should be Taylor series expansion around this root point. So, it should be the xk, and then we have x minus xk, then the derivative of this quantity at xk point and so on. If I take only up to 2, and now you look that this is a root. So, this quantity should be 0, because that point I already mentioned here, this one, that xk is a root and I am expanding my Taylor series around this root point, these points, and then this value should vanish. If this point vanishes, then we can have delta and then h x is equivalent to delta of x minus xk multiplied by h say prime and then xk, this one. Now, if you look carefully, this is a constant term, because I evaluate h at xk point, I evaluate h prime at xk point. So, this is a constant. So, I know that when we have delta function, and with a constant and x, it should be 1 divided by mod of a delta of x, that we proved last day. So, we are going to use this to find out, and in that case it should be simply 1 divided by mod of h prime xk and then delta of x minus xk. Okay. But this is done for only one root. For all other roots, what we get is the summation of the entire thing, because here we have 0 where delta function is meaningful, here we have a 0, the argument is 0. When h function is 0, that means the argument of the delta function is 0, and that is the meaningful point for delta functions. So, these are the points where we have the meaningful results. So, in order to get the entire picture, I should have a summation, and then it becomes simply delta of h x is simply summation for all the roots. How many roots are there, I need to calculate, and for each cases I am going to calculate this one under the condition that this is not equal to 0. This quantity what I am writing right now is should not be 0. If it is 0, then we should have other technique. For simplicity, let us consider this is not equal to 0, and we are getting this. So, this is a very important identity when we have a delta function. And now the next thing is to apply this stuff to find out some problems. So, what kind of problems one can, so let us do one problem. So, this is problem 3. In problem 3, maybe one can ask what should be the value of this quantity, the first problem. What is this quantity? I mean, how I can write this delta function, how I can write this delta function in terms of I will get rid of this argument, and the result is one can derive using whatever the expression I just wrote here. This is hx here is, so let me write it here. So my hx here, so my hx here, this function xs cube minus x, okay, xs cube minus x. So I need to find out what is my h prime, because every time I need to calculate it. H prime is equal to 3 x square minus 1. This is my h prime. Fine. Now let us find out what are the roots. So sorry, so h of x given as xs cube minus x, so it should have 3 root, and I can write it as x multiplied by x minus 1 and x plus 1. So the roots are, so the roots are say at minus 1, at 0 and plus 1. So we have a root here at minus 1, we have a root at plus 1, and this is 0. These are the 3 roots. So once we know the roots, then we are done. So according to our expression, we have delta h x is summation of delta x minus xk divided by mod of h prime xk. So that quantity I know. So for each cases, so the first case when xk is equal to 0, so I have delta x here, and the denominator, if I put, so what is my h prime, I should write here h prime x is 3 x square minus 1, that we already figured out, 3 x square minus 1. Now I put x equal to 0. If I put x equal to 0 here in this equation, I should have minus of 1 here, mod plus. What is the next value for next root? Delta x minus next root is say 1. So it should be x minus 1 divided by, I will put 1 here, then we have mod of 2 plus delta next root is minus 1. So I should have x plus 1, and again I should have here mod of 2. When I put this value 1, then I should minus 1, then I should have this. So eventually we have this is equivalent to, so delta, so finally what we get? Finally we get that delta xs cube minus x, which is a function itself, is equivalent to, if I split this into 3 deltas, so 1 delta function plus half delta function at minus 1 plus half delta function as plus 1. So now if, since you know this, So, I am giving you a homework, that is the last part of this today's work. So, this is homework, and please evaluate this integral minus infinity to infinity delta xs cube minus x, and now we have e to the power function like say x minus 1 dx. Okay, please evaluate this integration when we have a delta function having a function in the argument, in its argument. So, with this note, today I will not going to have much time. So, with this note I am going to conclude here. So, thank you for your attention and see you in the next class.